I actually did bring a copy of it.
Oh.
But we'll see how things go. We have a lot of the material we're going to cover today anyway. So my hobbies would be drilling access examples, which you all need to do anyway. So I'm not feeling so mad at you all right this minute. So even if we were to give you a pop quiz like at the end of the class, I'm thinking it won't actually be graded. But I'm going to give you some exercises to work on at the end of the class. So what I'd like to do today is explore this. Access is one of those things you feel out like doing, seeing what happens in a bunch of different contingencies. Maybe I could invite some of you up here and say, maybe I'll do it that way. Instead of having you all do it, I'll invite a couple of you up here to try to solve the problem. And then I want to get into this relationship that I've characterized a bunch of times sort of informally, that is like, what is exactly is the relationship between this thing called consensus that we've been looking at for the last week and a half, and this idea that we touched on in the very beginning of the class, like the second week of class, and said it's too hard, we're not going to give you an implementation for this thing called totally over broadcast. I kind of hinted that you might want to use this to implement this. It turns out that the relationship between these is more subtle than that, and interesting. And I'm going to make an argument by reduction that they're actually equivalent problems. And this is to say this thing is solve more than solve two. Totally over broadcast. Then I'm going to introduce an optimization, a practical optimization of the package algorithm that we've studied up until this point that makes it something that you would actually use in practice that isn't dog slow, that you could actually use to do interesting things. This is something called multi-paxos. Any implementation of Paxos in the wild is actually an implementation of multi-paxos, but it makes sense to stage the discussion in this way. First, let's describe a very simple protocol. Lamport actually called the protocol we've studied so far the Synod protocol, not Paxos. The Synod protocol chooses one thing in a fault-tolerant way so that everybody agrees. Multi-paxos does what you all have pretty much intuited we're kind of going towards here, which is choose a totally ordered sequence of things of arbitrary length. Right? This seems like a useful tool to build systems with. This doesn't. But it should be easy to convince ourselves that if we had one of these, we could. If you can choose a thing, and you have a gadget that chooses a thing, you could probably choose a sequence of things. We'll talk about how that would work. And we'll spend a little bit of time on something that I feel like I have deprived you of in this class, diving into the theoretical material of consensus so early, which is spending a little bit of time going slow, talking about what the hell consensus is for. Why would you do consensus? That sound good? Great. Should we do the Paxos drill block? Yeah, let me show you some of the things that I was maybe going to quiz you if I came here and just looked at you in the face and decided I hated you all. I should have seen me. I was in my office on my whiteboard, and I was like, oh, this won't show up. You're going to see this picture a lot. What if we had a ball? What do you think happens next? Think about it for a minute. Don't call it out. Anybody think they know what happens next? Take a minute. I want to make a point that what I'm trying to show you is that like this process is dying here. So it can't do anything after the acts. But obviously it would do some things here. So it's not like this is the last action you see of this process. He's going to try to send out this accept. And also this process is going to try to send out this accept. So first of all, do you buy that this execution can happen? Is this like an impossible execution on the basis of the protocol that we've already studied? Buy it? Yeah, I think this is a possible execution. And I think there's only one possible outcome in this case. Remember at the end of class last time we looked at this execution where two things can happen, resulting in two different outcomes. And the only thing that distinguished between the two was the order of messages delivered. So that was kind of weird. I don't think this has a, if you think you know the answer, I'd like to invite you up here. Yeah?
Okay. So.
Thank you. And maybe I can have another color? Maybe? No. It would be cool, but. Yeah, show me the emanations from P1 and P2 and what their outcomes are.
Well, so as soon as we hit this point, P1 is going to send the do message.
That's correct. So the accept message we call it, and that's because P1 knows that she has a majority of acceptors who have agreed to do whatever she says as long as.
Right, and so that message is going to go out and it's going to hit A1 and A2, presumably.
And yeah, and possibly A3 too. But yeah, sure. Let's just say that.
And A1 maybe will send the acknowledgement back like yes, 1.1.
Yeah, and in fact, like I have totally accepted that.
Right.
I've updated my accepted value, my accepted proposal, and so on.
Right.
So you can show that, Eric. Go ahead.
So,
I mean, it falls on deaf ears, maybe, but yeah.
Okay. That's going to fail, but
it would have said 1.1. Yeah, totally.
1.
Good.
Right, and then A2 is going to send back a message that also is not going to get there, but it would say 1.2.
Excellent. And then over here?
And then over here, this message, absent any other input from another proposer, P2's acceptance message, there's going to be 1 to A3, and then that one's going to say, okay, sure. And then there's going to be 1 that goes out. And it's going to only end either before this acceptance message or after. And it doesn't really matter which.
It doesn't matter, right? It doesn't change the protocol behavior. And then, so this, no matter what happens, A2 will reply 1.2.
Right.
At which point, let me just finish the protocol for you. And it doesn't matter where this touches down. This one will say 1.2. And at exactly this point, this is like the commit point, right? P2 knows that Y was chosen. And although some other proposer might come along with a very big number, this proposer will definitely propose Y again. Why? Well, because for this proposer to prepare their proposal, they have to talk to a majority of acceptors, and at least one of these acceptors will be in that majority because every two majorities overlap. Right? You want to do one more like that? I have one more that I cooked up in the lab.
Why is A2 sending to P2 1.1? A2 to P2. Okay, 1.1.
No, okay, no, nothing.
Oh,
It's
no.
Let's see here.
an empty thing.
Actually, this is what I wrote down, but I like this one better. What do you all think happens here? Think about it for a minute. Somebody else can come up.
This first message from P2 is the prepare message.
Sorry?
This first message from P2, that's prepare.
This is, there's only the one message that I've drawn in.
Right.
That's a prepare message.
Yeah.
It's always, the first message is always going to be the prepare message.
P1 is also supposed to send another one to A2, correct? Since it also asks A2 if it was okay to send the data.
Oh, sure. Let's imagine though that you mean like an accept message to A2?
Yeah.
Yeah, but let's imagine that it didn't make it.
Okay.
Yeah. You want to come up and do it? Question.
I mean, you can answer, but
What?
I'll go.
So if you have a question, ask it. I'm happy to answer it. If you have an answer, please come on. And thank you.
Because there's two possible outcomes.
Cool. I know that makes things hard for you, so maybe pick one and draw it, and then we'll decide if we want to just describe the other one or if we want to draw one too with some erasing.
So everything over here is good. So this is gonna say.
Oh, sorry.
It's gonna say like, okay, you're all good, and this one's gonna say okay as well.
Unconstrained.
Right.
Okay.
And then this one as well. But it's going to say you're constrained. You need to do X.
Yeah, for 1.1.
Yeah, for. Right.
Yeah. Okay.
And so depending on the order these touch down in, we will either need to send out an accept of X, or we can send out an accept of whatever we want.
Nicely done. And this is sort of the example we studied before.
Yeah.
Right?
And then we'll do that.
Do you remember why I argued? So the fact that we could go either way, it follows directly from the fact that X was not actually chosen.
Yes.
It was just accepted by a minority. Why do we have to propose X if we see this message first or second?
Right. Well, let's say this message never got to us, but A2 did actually accept X.
Excellent.
So for all we know, there could be a majority out there. So we
Exactly.
have to assume there.
That's exactly right. So we have to conservatively assume if we see even one accepted value, that might have been the accepted value on the one node that is in the intersection between our majority and the other majority that got the accepted value. Right? And that might not be the case. Yeah.
So in the case where the okay, but you're constrained message comes down last.
Right. Well, in that case, we know, because we've seen a majority of people who didn't accept it, that in fact it was not accepted. We can propose whatever we like.
Okay, so that's the case where we can propose whatever we want.
Right.
Okay.
Yeah. But in the event that this one came in first, well, the other thing we can do is wait for the third. But because in general, we want to go fast.
Right.
And we know that it's safe to propose something that's already been accepted by one acceptor as long as everybody eventually accepts it. That's what we do. Because the other reason we don't wait is we might have to wait forever.
Right.
A2 might not be coming back. Questions? Yeah.
So would you say that the commit point, the point at which there is consensus on X, would you say that that's the point after which P2 hears back from one of A2 or A3 because it knows that A1 already accepts X?
Wait, say it again.
So P2 then will go on to say accept 1.2 S to A3 and A2.
Well, that's an interesting question.
Is it consensus after A3 or A2 accepts, or does it need to hear from 2 in total?
I'm going to say that it needs to hear from 2, but I don't have in my back pocket the counterexample of where it could be bad. The thing that gives me pause is let me think about it. Like, you're proposing an optimization, the flavor of which is at the point at which I get the majority. No, that's not true. The concern is that it might not actually be X in the end. Because if X was only on one server, some third proposer might come along and set it to something else. And we have to make sure that our proposal passes. So the midpoint isn't really germane, but I want to make a distinction between when we say in the very abstract that a particular proposal is chosen or decided is when it is accepted by a majority of acceptors. Now, that state of being could only be perceived by a godlike being, right? So there's a difference between a value being chosen and some one process knowing it, right? So in this example, let's see. So accept 1.2 X, let's say they do. this accepts it, and this accepts it. We say, in some sense, that it is chosen now. But it's only when these two things come back with the same proposal number that P2 sent that P2 knows it here, and P2 is the only process that knows what was accepted, which brings up another subtle point, which is like a practical implementation of Paxos will need a few other little protocol bits layered on top of it so that other people, the acceptors, for example, and the other proposals can learn about the complete set of chosen proposals. Yeah?
So isn't this actually a counterexample for that optimization, where we could say that as soon as we get the constrained response, and we know we're going to choose that, we could say that, okay, that's the commit point, except what happens then if P2 crashes? We're still in this case where another process.
Great point. Because
Because that happens with P1.
if we said the commit point was here, what happens if the crash point is there? And we're in this position like we were with the single acceptor where something's been accepted, but nobody knows, and we can run afoul of agreement very easily. Thank you very much for that. Yeah, and thanks for the question. Good? Questions? Paxos? Paxos isn't so bad, right? Cool. Oh, and we can do more, and I'll send more, and things like that. I want to talk about consensus and its relationship now with this elusive fully ordered broadcast idea. Remember that consensus can be sort of abstractly viewed as a gadget with the following shape, distributed across a bunch of sheets. It has some number of inputs, it has an output, everybody has to agree about the output has to be one of the inputs, eventually it has to poop out an output, there you have it, that's consensus, right? Totally ordered broadcast is a slightly different thing, right? In some sense, you can think about totally ordered broadcast as it's this abstract array of slots. There's the 0th slot, and the first slot, and the second slot, and so on. They establish total order mapped into the integers. And as processes are sort of sending messages to each other in the network, we have somehow slotted in one message into each slot. M1 got slot 0. M27 got slot 1. M506, for some reason, got slot 2, and so on and so forth. Right? It's this magical thing that these things are flying, they're touching down on different processes in different orders, and yet somehow all of the processes will know to deliver them in this total order. Right? Ruling out this bad thing. Were there such a protocol, this picture wouldn't be problematic. Because let's say that this was A and this was B, this will establish that both of these things either deliver A then B, or B then A, and we don't care which. Right? You can all race and try to get in there. I just want mutual exclusion on the slots. One message per slot, exactly one message per slot, please. And I'm arguing now that these two gadgets are equivalent. They're the same thing. So in computer science, when we argue that two algorithms are the same thing, how do we do it? That's correct. So, anybody have some thoughts about how we could? We're going to have to show that if you had one of these magical things, you could use it to do this, and the reverse also. Does anybody want to try it in one direction or other? Yeah.
So, we can use consensus to implement ordering by coming to a consensus on which message came first.
Yeah, or in some sense, you could imagine another way of looking at it that's essentially equivalent is to say, we can just do this. So we have these slots, and they're numbered. The only thing that's uncertain is what goes in each slot, right? So in the presence of very many messages, we can view those messages as the inputs to one of these gadgets. Any given message, message 1, message 2, and message 3, let's say. And so we implement one of those gadgets in every slot, right? So this is 1, 2, 3. And we know due to the rules of consensus that what's going to come out of this is either 1, 2, or 3. Let's just say it's 2. Okay, fine. Now we can move to slot 1, implement another consensus gadget. Now the inputs are 1, 3, and possibly 4 has come along. I don't care. Maybe it's just 1 and 3. And now maybe it says, I don't know, 1. We move to the next one. You see? I'm not saying that this is an efficient thing to do, but you could do this. You have a gadget, you choose a thing, you statically allocate it in a bunch of slots, and you do the thing for each of the slots. We can use consensus to implement totally ordered broadcast. That shouldn't surprise you, I've already told you. What about the other way around? Yeah.
You can just pick the first message.
Nice. Yeah. If I had a totally ordered broadcast gizmo that just worked, and I wanted to get consensus on a thing, I could say, okay, everybody who has a proposal, fire it into the network. And whichever proposal gets delivered first, that's the one that we got consensus on. There can only be one thing in the first slot, so that satisfies agreement. Every slot, no slots can be empty. That satisfies termination. I only put things in the slots that were messages. That satisfies validity. Right? Yeah. That went fast. You believe that? We're the same thing. And it's going to turn out that we understand how to implement this, and we're going to use it to implement this and not the other way around. Okay? Okay, good, great.
Okay.
What? What's so funny? Okay. Oh, you know what? If we do run out of time, we could also talk about causal consistency and key value sources.
What was the last one you said?
Huh?
You see kind of mumbled me in.
Sorry. If I run us out of time, instead of sending it home early, we can talk about causal consistency and key value stores. That's the only thing that's relevant.
Maybe
about
topical.
Yeah. So, good. Okay, so let's talk about how you might do this. What changes will we need to make to our protocol to do this?
You have this dependency thing where you can't put a message that is accepted into the next slot, into the next consensus thing.
What do you mean?
Like 2, once you've chosen 2 for A, you can't put it back into the device for slot 2.
Sure.
Just, I don't know.
Like if we wanted to just take Paxos and add some stuff to it so that it could do something a bunch of times, arbitrarily many times, rather than just once, what changes do you imagine that would make to the protocol? Are we going to do a completely different protocol, send different messages, or are we going to send messages with different contents? Or
Decide monotonically increasing numeric number values as we go along.
Yeah, so like, at least let's do it as a straw man, and this straw man is going to turn out to, I think, just work. But then need to be optimized to be fast. Instead of saying, you know, I want to propose proposal number 1.1, where those numbers just mean it's just a nonce, right? You know the term nonce? Number used once. So that's just a nonce, right? But we also would like to propose it for, you know what I'm saying, a slot, right? So you can imagine saying, we're just going to add the slot that is relevant to our prepare and accept messages. Maybe we only need to add it to one, but let's just through an abundance of caution, let's just pass that around, right? So we do our normal thing and say, okay, prepare this, okay, now I'm going to ask you to please accept for slot 0, my round number is 1.1, and then you imagine the way the Paxos protocol works is this number changes slowly relative to this one, because you need to keep picking a new one of these. You might go through a great many rounds trying to decide on one slot, as we saw. In fact, Paxos could literally run forever trying to decide on one slot. So in a lot of executions, we're going to expect this number is going to keep climbing while this number stays the same. But in the happy case where everything works, we're going to see executions like this, where these people say, hey, these people said I'm unconstrained, not a problem. These people all say no. And in fact, usually it's going to look like this. Usually there aren't only proposers. There's one proposer and everybody's happy, right? These people say cool 1.1. And then this person says, great, now I know what's in slot 1. At this point, I know that slot 0 is done, and I know that I forgot to say what I was proposing, X, right? And I know that X goes in slot 0, and now I can be like, okay, maybe I'll just pick a new number, or I'll use the same number. I could probably use the same number, but I have some number. I do it for slot 1. So that'll work, right? What's wrong with that? Why is that not a very good protocol?
Do you mean aside from it being slow?
No, mostly the slow.
Okay.
Yeah.
It's slow as well.
For different slots?
Well, I don't want to go there. You could do that. And Lamport actually suggests that maybe you would do that.
you say?
He said, hey, you could propose multiple concurrent values for different slots. And you could. But the thing is, let me put that on the stack. Because when we get back to practical applications, it's going to turn out that that's not particularly valuable. Most things that use Paxos want to do things in order. Most things that use Paxos, for example, are implementing state machine replication. And what they're doing is they're deciding on the total order of transitions to feed to all the replicas. That doesn't do me very much good to know the values of these slots, because I can't apply those commands until I've applied the complete prefix. So you're absolutely right. It's of questionable utility in practice. Yeah?
Well, you'll burn through all the slots in the case where you crash over slots. Like if you have P1 and P2 both trying to write, and then you have P1 trying to do slot 0, and P2 trying to do slot 0 as well.
Well, I mean, we've had those conflicts in the case of the Synod protocol as well, right? So like, this protocol, multi-Paxos, is not going to do any better at the dueling proposers case we would expect than Synod would. In fact, because there's more going on, there's probably more that could go wrong. But I think maybe the big takeaway from this is that this is a two-phase protocol that requires 2 round-trip times to the servers. Paxos is often used to implement geographical replication, where you're actually replicating data in a strong and consistent way between like the US and China or something like that. And so like, the WAN latency between the US and China could be, I don't know, what do you think? What do you think WAN latency between the US and China is? Ballpark. Within an order of magnitude.
About 200 milliseconds.
Yeah, 150 to 200 milliseconds. Let's say it's 200. Nice.
Online gaming.
What's that?
When you play online games, you feel it.
Interesting. There's a great cheat sheet that Jeff Dean, the Google guy, wrote. It's like numbers that every engineer should know, that are just compare the relative orders of magnitude of common operations. It's good to know. So, but that means that if I have 2 round trip times, how long does it take me to commit a value in the US and China?
800 milliseconds.
Yeah. Long enough that a user can see it and be like, wow, that's slow. It sucks. That's not good. And then we ask ourselves, well, why are we doing 2 round trips again? Like in this happy case where there is no P2, let's imagine for a minute. Like, what was phase 1 for? Phase 1 was to find out if there was something already out there, which is only the case if there was some other proposer who has not completed what they were doing. That happens, you have to deal with it, but it doesn't literally happen every time. And the other reason is to get a majority of people to say they'll do what I'm going to do. So it's tempting to ask, can we just throw away the prepare phase? Well, we know we can't just throw away the prepare phase, because we saw in an earlier lecture, if we tried to do this in one phase, how it didn't work. But can we most often throw away the prepare phase in the common case? And the answer turns out to be yes. So let's see if I can do this in a tidy way.
Just send an accept with your number. And if it comes back with that number, then it is accepted.
Exactly. So but having first prepared, because that's the first thing a proposer does when they come into being, they're going to have to get a cadre of acceptors to agree to be their flunkies. Right? There's no avoiding that. So I wake up, this is my first act, I say, I pick a number, just like we learned, and I do regular synod. But once I have a majority of acceptors following me, I can nod and say I did for every future prepare phase. And I'll know if I screwed up, because I'll learn about a number that I didn't suggest. So for example, I'll go, okay, accept at 1.1 for slot 0, please accept X. These guys are like, cool, you got it, 1.1. Okay, thanks, like now please just accept still within 1.1. Now this isn't changing and the other thing's going up. For slot 1, please accept 27. It's like, cool. And if, God forbid, some other proposer came along, picked a higher number, da-da-da-da, one of these is going to come back and be like, the thing is 1.2. Now what should melody proposer do?
Increase the number and
Drop back to, well, either back in the law is an option. But the other option is pick a new number, higher than 1.2, start again at phase 1. This is known as multi-Paxos. And this is like what you do, right? It would be crazy to do 2 RTTs all the time when you only need to do 2 RTTs in the worst case scenario and nice way to think about it, but it's going to cause some confusion if you stick to it too tenaciously, is that in some sense the prepare phase is like a soft leader election phase. What's the pessimal scenario for multi-paxos? There's two proposers. If there's two proposers, even if they're not in a perfect synchronization storm, like we saw before, even if the thing isn't going to non-terminate, the expectation is that the Paxos protocol will take 2 RTTs rather than 1 for pretty much every time. And that's bogus, right? Because in general, you might want to use multi-Paxos, and certainly when I first started studying this is what I wanted to do with it, to have a multi-master write-anywhere kind of replication system, right? Where if all these people are proposers and acceptors, and they know how to do consensus, it's my initial, and they know how to do consensus, then you can imagine that like client 1 could go ahead and do things to this person and find out if they succeeded, and client 2 could go ahead and do it. Like we don't care where the writes happen. And so we don't have to worry about a single server bottleneck like we saw on primary backup. You could just kind of write anywhere. It doesn't work. It doesn't work because the clients aren't directing their writes to a single server. This optimization doesn't apply. Right? This is a 2-round protocol. Whereas if everybody is sticky with a pseudo leader, it's a 1-round protocol. Do you see what I'm saying? Does this make sense? Right? Because let's imagine that this person successfully prepared and got everybody to follow them with 1.1. That's great. And now, every time a client wants to do something, they can just do 1 round trip. Like now, basically, we're doing something that looks like primary backup. Hey, accept this. Hey, they accepted it. Hey, accept this. Hey, they accepted that. Somebody comes along and prepares something out here, 1.2. All of a sudden, the arrows change direction. Now people are following this guy. This guy had to do 2 RTTs to get that thing accepted. And if everybody keeps directing things to them, we're cool. But if we keep jumping around, we're screwed. That stinks. Lamport's answer to this, which is also Lamport's answer to the dueling proposal problem in general, is you should also implement a leader election protocol. Not to be confused with what I was calling soft leader election. The idea being that if we had some external to Paxos mechanism that made it extremely unlikely that there was more than one proposer at the same time, we would usually be in the 1 RTT. Happy case. And Lamport sketches a really simple protocol. You're going to read this in your reading that's coming out like today. He just basically says, proposers periodically tell all the other proposers who they are. And the leader is the proposer with the lowest ID number from whom you have heard recently. Something like that. After some other side. Right? So proposers always talk to each other. They share their identity. Everybody knows the lowest numbered identity. You forget about people from whom you haven't heard in a while so that you don't think a dead node is the leader. So in this scenario, like P2 and P1 would be talking to each other from time to time. And P2 would know that there was a P1 who was periodically heartbeating them. So P2, if a client came to P2 and said, hey, can you set X to 1, what would P2 do? Similar to what we would see in replication? It could forward it, or it could say, like, dude, the P1 is actually the heartbeat. You should just send it to them. It could do either one. Right? Yeah?
Is a heartbeat just like pinging another node to make sure they're still alive?
Well, the distinction I would make, I mean, it's the same basic idea. But, your heartbeats would be sort of push-based, right? Where I'm saying, like, Alice is, in order that Bob knows she's alive, periodically heartbeating him. That's a heartbeat. Whereas the pull-based version of it would be like, Bob periodically asks Alice if she's alive, and she says yes. This would be ping, this would be heartbeat. But they would achieve the same thing. Where was I? Right, so P2 knows about the existence of P1. P2 could just not propose anything. Yeah?
Okay, so the proposal step wasn't necessary, it was just to reduce the likelihood of this race condition thing happening.
Well, no, the proposal step was necessary because if that race condition happened, we violate agreement. The prepare phase, yeah. It was necessary. It's just not necessary in the interval between this accept and this accept. Because if somebody else does come along, this thing won't get accepted, and I'll know. Right? So there's no harm once I've prepared something, as long as when I hear back that my thing wasn't accepted, I sort of straight in. Well, that's the part I'm not understanding, because like in general, when we talk about race conditions, the reason we're concerned about race conditions is that they can affect our agreement property, they can affect our consistency or something like that. And so avoiding an anomaly, I would think of as an optimization. Require property in the protocol.
So then agreement breaks if you have two concurrent proposals, exact touchdown at the exact same time.
Agreement, nothing in any of the protocols we've seen will violate agreement. It would only violate agreement if we skip the prepare phase maybe altogether. And we need to go out and see if anything was accepted out there. And then once we've done that, we can make as many requests for acceptance as we like until we've learned that somebody else is blowing us up. And that has to happen. So in the event that P2 waits a certain interval and hasn't happened from P1, and all likelihood P1 is down, so P2 can start making proposals. Now, wait a minute. I thought I told you that you can't implement a failure detector that works. Any failure detector we implement due to asynchronous communication is going to have false positives, right? So if our failure detector has false positives, that means that our leader elector is going to violate agreement, right? So leader election 2 is an agreement problem that attempts to satisfy validity, agreement, and termination. As we saw, leader election privileges termination over agreement, which means that you could have multiple leaders. That would happen in the event that P1 was up, but its heartbeat for some reason got delayed, and P2 decided it was the leader. Uh-oh, now there's 2 leaders. Is that bad?
It's just a little slow for a little while.
Who cares, right? Because Paxos Synod protocol guarantees agreement, even if there's 1,000 leaders. Paxos privileges safety over everything else, and that means that you can take an inconsistent leader election protocol and layer it on top of Paxos as a performance optimization. I don't care that the leader election protocol doesn't always work, as long as it's fastish. Does that make sense? Because we've already seen that if there's 2 proposers, what's the worst thing that could happen? It never terminates. But we know that we can decrease the likelihood of it not terminating to almost 0 using these techniques. Everybody with me? Awesome. That multifaceted. Paxos 4. We talk about that, or should we just do causal consistency? I'm sorry, 20 minutes left. Now let's talk about practical applications, since I haven't really done that much. All throughout the class, I've mentioned, like in an offhand way, oh, and you could use consensus for that. Anybody want to remind me what some of those things are? What do people use these things for?
Distributed ledger.